Welcome back to part 2 of the Apple III repair extravaganza. Last time we had Unit 2 on the bench, this happened. Big fat nothing. Now that it's back on the bench, let's dig right in and see if we can get it working. First things first, replace the power supply. Next up, system diagnostics. Unit 2 passes with flying colors, so let's get Unit 1 back on the bench, because I think it's still got some problems. First things first, we have to deal with this missing keyboard controller. My solution is this. Let's zoom in and I'll tell you all about it. This is a replacement keyboard encoder for the Apple III computer. It's actually based on the keyboard encoder that is built into the keyboard for my JCM1 computer. Code is almost identical, it's just been optimized a little bit for speed and modified slightly for some of the requirements of the Apple III. This perfectly emulates the Apple III keyboard controller to the point that the Apple III Diagnostics, the dealer Diagnostics, can't tell that this is not a real controller. Everything on it passes. Awesome sauce. It's based on the PIC16F18875 microcontroller, which is basically the only PIC that's out there that's inexpensive and has enough output pins to do all the same pins in the original controller. And, you know, I use that because that's what I used to develop the JCM1 keyboard, so it just made sense to use that chip. This will replace that keyboard encoder in any Apple III. It'll also do the Apple III Plus with a slight firmware update. And on top of all that, here's the kicker. This will also replace the keyboard encoder in an Apple IIe. With the right firmware, this completely and perfectly emulates a default off-the-shelf AY5 3600 keyboard encoder from General Instrument, or the common replacement, which is the KR 9600 Pro. So if you have any of those machines, you've got an Apple IIe, an Apple III or an Apple III Plus, and your keyboard encoder is bad, you can pre-order one of these right now from my website, jcm-1.com. And when I get enough orders in, I will put it in order for parts for more of these PCBs. I'll get those in, and I'll build them up, and I'll start shipping them out to people. Now, why did I decide to go with this instead of just buying, like going on eBay and buying a chip? Well, similar reason to doing this little hackadoodle right here. A lot of the chips you're going to find on eBay or wherever are going to be pulls. They're probably also going to be bad, so I'm going to waste my time and my money. And finally, if this chip is working in another Apple III, it needs to stay in that Apple III. There's nothing I hate more than pulling good chips out of working machines or even partially working machines to throw in another machine to try to get it to work. Just make the original machine work and preserve everything. So if you've got totally bad chips and you don't have a good replacement chip, I say design a replacement, and that's what I've done here. So let's get this popped into the Apple III, run the dealer diagnostic, and make sure everything else is working okay with this system. And of course, what test are we going to run first? The keyboard test. And everything here is in shot, so you can tell there's no tricks up my sleeve or anything. We got this keyboard attached with this cable right here to this machine with this keyboard encoder. And I'll even unplug the video so you can tell this video port right here, so you can tell it's all the same setup. No tricks or sleights of hand. So let's go ahead and do it. Test passes. Awesome. So let's go ahead and run the rest of the tests. Great, all the tests pass. But I'm not convinced everything is solved with this machine. You see, when you give it the good old three-finger salute, the Control Open Apple reset, from this screen in the dealer test, this is what's supposed to happen. Instead, this is what actually happens. Something's definitely not right there. So I guess that means we need to go back to the schematic. So we're going to take a little detour here before getting into why the computer doesn't reset correctly to look at all the bits and pieces of the keyboard schematic. I've stared at this enough times for long enough that I've been able to decipher what every little bit and piece of this keyboard logic does, and I just find it fascinating. So I just want to run through it, just to understand what it does. So this here is obviously the keyboard encoder chip, which is this chip up here, which you can't see, which does all the actual scanning of the keyboard and sends the data out to the computer of what button's been pressed. This section right here, this circled section, this has to do with the key repeat and key repeat speed. This detects how long a key has been pressed down and when to start sending the repeat sequences out to the computer. It also taps off this line right here, which, as you notice, is one of the Apple keys over here, and that's the solid Apple key. On the Apple III, when you hold down the solid Apple and then press a key, it increases the key speed repeat. Or key repeat speed. So, of course, that's going to tap into this circuit so it can detect that that's down and then change the speed of the repeat. This is the keyboard strobe. Basically, this represents a single memory location in the Apple III that the Apple III can read to go see if a key has been pressed down. And of course, it's got the clear strobe light here, or clear strobe line here, so the Apple III can touch that line and turn this latch back off so it knows, hey, I've read the key, I don't have to deal with it anymore. This also deals with intercepting all of the information coming off of all the data ready lines and any key down lines and all of that stuff to send out this line here, which is the keyboard interrupt line, because the Apple III has interrupt control. It's a little more advanced than the Apple II. So that handles that. This right here is what I would call the keyboard selection address latch thing. Basically, this allows you to select what in the Apple III documentation is called the A bus or the B bus, the A keyboard bus or the B keyboard bus, to determine what data actually gets put onto the data bus when you read the keyboard. What that means is, depending on the selection of these two lines, you can select either whether you're scanning for the ASCII keys or whether you're scanning for the special keys like Control and Open Apple and Control or Open Apple and Closed Apple and stuff like that. So that's what this section does. But now we're going to get down into the meat and potatoes of why we're actually here, and this is the reset parts of the circuit. So we'll move this a little centered for you so you can see it better. And there's two major reset circuits in the Apple III. This reset circuit right here, in this big squiggly area, is what I would call the hard reset or cold reset. This is what happens when you give it the old three-finger salute. And this section would be the warm reset, which is similar to on the Apple II, just control reset, or in this case on the Apple III, just pressing the reset button. It's the kind of the warm reset that okay, I want to get back to the prompt, or my program is hung, I want to get back to what I'm doing without resetting the entire computer. So that's what this section does. There's this little interesting circled section here, which I'm going to get back to in a second. So in order to figure out why this Apple III is not doing the reset magic correctly, I went ahead and did my trace trick here of tracing all the lines coming from the keyboard into the circuitry of the computer to see where everything goes so it can figure out what conditions might be setting or not getting set to cause the computer to not do what it's supposed to do. So we've got the control line here, and we've traced it down, and it goes into the 74LS139 chip. And we have the reset line, the red one here, which basically does the same thing. Now let's dig in a little bit further to this. We know that control, well, I'll step back and say we need to know whether or not the keyboard itself is actually sending the signals to the computer. We know that it is, because if we just hit reset, the computer does something. You know, it's picking up the signal. And we know that the control key and the open Apple key work because the keyboard test passed. The dealer diagnostic test actually tests these keys to ensure that on the programmatic side over here, on the data bus, it can pick up those signals. So we know the keyboard latches are working correctly. When you press the button, it's sending the signal out. No problem there. Okay, good. So that means our problem is a little, it's a little more closer to the hardware, so to speak. It's closer to the metal. It's not a programming issue or anything like that. There's something else going on. So when we trace these lines down, the common denominator keeps coming back to the 74LS139. Now, what is this? This is a 2 to 4 encoder. Basically, we can take 2 address lines in, and then it will send out 4 signal lines to determine it determines the how can I put it? The decimal equivalent of the binary number. So like if these are both 0, right? None of the output lines will be lit. If these two together equal 1, like address 0 is on and this one is off, this will add the output of this will equal 1, and so on and so forth, until all 4 lines are lit up, basically. If you want more details on how that functions, go read the data sheet. So looking at this latch, or looking at this 139, let's look at what it's doing. It has address 0, address 1. This line here, which is hard to read on here, but this is the enable line, which enables this to even do anything. And only one of the 4 outputs are actually tapped off of this chip. Output 11. Now, looking at the data sheet and the truth table, in order for this to be lit up, in order for 11 to be lit up, A0 needs to be high and A1 needs to be low. Also, 15 here, it's G in the data sheet, also needs to be low. So if we trace this back, this low line is the reset key. And as we see, because it's got the bar over the name, that means this is a low, active low signal. So that activates that. The control line with the bar over it also means active low. And I already know, because of the way the binary output should be of this, this needs to be active low with this line being high to make this turn on and do a full cold reset. So we know that all of these conditions are being met. Now I'm going to come back to this condition in just a second because it's very fascinating. We know that all these conditions are being met, yet this line isn't getting pulled correctly. Because when we can meet all these conditions and try to reset it, it's doing a warm reset instead, and not a cold reset. It's not doing a full reboot. It's just like, it's the 2-finger salute instead of the 3-finger salute. That makes me think that one of 2 chips are bad. Either this latch is bad right here, or possibly, this line is bad, right? Or this inverter chip is bad. Now, based on what we know about the layout of the computer, I'm going to move this real quick. And I'm going to move the camera. Sorry about the shaky cam. This chip right here is J11. J11 is right here. Now you remember the other chips that I had to take out right in this area and clean them? And you can remember this chip is failed completely? If that's right there in that same area, yeah, probably a problem with corrosion on the pins, or the chip is bad, or something like that. So why don't we just yank that chip out, clean it, put it back in, and see if it solves our problem. If it doesn't, I have 74LS139s in my bins. I'll just replace it. Now, I did want to go back and talk about this little part of the circuit right here, because this is fascinating. I'm going down the rabbit hole again, but bear with me. We know that all these conditions have to be met. These three conditions have to be met for this signal to latch. What is this signal here? It's very interesting. I went through all of the schematics of the Apple III, and I could not find this signal being represented anywhere else in the schematics. The signal is called reset LK. That sounds to me like it's reset lock. It's also active low, which means when this is inactive, this line must be pulled high because it's an input, you see. You can't have floating inputs on digital inputs. So this has got to be pulled up somewhere by a resistor to high. Fascinating. But it's not mentioned anywhere in the rest of the schematics. Nor is there actually any place in the schematics that show that this is actually pulled high. In addition, this has to be an input. It has to be selected somewhere because, as you can see, it comes up through here as an input to this part of it, of the schematics as well, the warm reset. Reset lock? Here's my theory. I wasn't able to find any documentation on this. Maybe I didn't search well enough, but my theory is this. This was designed for, I don't know, educational institutions or something to that effect, where a key switch, a turnable key, could be installed maybe in the back panel of the computer and connected to this line somewhere on the board to allow a teacher, instructor, something like that, to actually lock out the reset function. Or maybe if the Apple III is working as an industrial control system, maybe they were planning for that, you could have a key that you could put into the computer to lock the reset function so some idiot couldn't come by and reset it when the thing was running a factory. You know, the manager had to come up and put it in there. Or maybe it was designed in the case of let's say if you were using it as a cash register or something dumb like that. Again, you would have a manager's key to prevent somebody from resetting the system. Yet, there's no documentation anywhere of that. I just found that absolutely fascinating. So we know that has to be pulled high. It's pulled high somewhere. It's just high all the time. It's just what it is. So anywho, back to the actual game here. I'm going to go ahead and try cleaning this chip, this LS139 back here, and potentially replacing it and see if that solves our problem. Bad chip. Bad! Well, that 74LS139 ended up being bad. I had to replace it. But with that replacement, I believe we have all of the hardware on Unit 1 fixed. So let's just double check it to make sure it does what it's supposed to do. Yep, it is working perfectly now. All the hardware on both units, at least for the electronical part of the hardware, is functioning. So that means the next step is we get to clean up both units and restore them and get them looking like they were brand new. Well, that was fun. We got to save 2 old computers from the landfill, hone our diagnostic skills, and learn a bit about the Apple III in the process. Thanks for hanging out with me today. Remember to like, subscribe, and ring the bell to stay up to date on my latest adventures. You can also support me through Patreon or by snagging one of these cool keyboard encoders from my website. Links in the description. Well, that's all for today's episode. While you're here, check out some of my other videos, and remember, 8 bits are all you need.